Hi, good morning. I'm Donny from Children's Hospital of Philadelphia. I'm honored for the invitation to speak in such amazing conference of the three big giants in the field. So I feel quite humble and thanks so much for the opportunity. We performed exome sequencing, deep exome sequencing, and different panel sequencing in a cohort of complex lymphatic anomaly patients, including CCLA, KLA, GRA, and GSD. We have identified multiple genes and observed resorption is emerging, which supports for therapeutic development. As many of you may know, central conducting lymphatic anomaly has significant clinical overlaps with other lymphatic anomalies, generalized lymphatic anomaly, capsiform lymphangiomatosis, and Gorham-Stout disease. CCLA is characterized by abnormal lymphatic channels if you would compare to other complex lymphatic anomalies. It was first described in 2014, and currently treatment option is limited, including surgical minimally invasive approach such as embolization. Our goal is to identify new genes for rare complex lymphatic anomalies. For some pedigree with multiple affected family members, germline variant would be highly suspected, and also because Noonan and Noonan-like patients occasionally have a lymphatic anomaly, we do standard exome sequencing with 60 to 80 folds for germline variants. And we also perform deep exome sequencing for those patients with the tissue available, 300 to 500 folds to target somatic variants with the variant allele frequency greater than 2%. For unsolved cases, we also performed ultra-deep targeted panel sequencing, which aim for somatic variant with even lower variant allele frequency. We then use in vitro cellular model and the in vivo zebrafish model to learn how this mutation affect the signaling pathway and explore potential targets for therapeutic development. But due to time limit and other colleagues will talk more about it, I will not discuss this part in depth. Through exome sequencing in CCLA, we previously described the germline variant in FNB4 in a four-generation family with a central conducting lymphatic anomaly. We modeled the mutation in cellular assays and in zebrafish. We observed mTOR activity was upregulated. Interestingly, zebrafish Maflino knockdown study demonstrate the lymphatic vascular misbranching phenotype, which can be effectively rescued by both mTOR and MEK inhibitors. Similarly, we also described a ARAF somatic variant in two additional CCLA patients. The gene is X-linked. In a male patient, we were lucky to identify somatic variant through exome sequencing. Modeling the variant in primary endothelial cells showed the variant altered actin skeleton and weak adherent organization, which could be fully reversed by inhibition of MAP kinase signaling. Similarly, we observed MEK inhibitor can rescue the phenotype in zebrafish model. Then a MEK inhibitor trametinib was successfully applied to the male patient, resulting in significant clinical improvement, whereas the patient was previously unresponsive to sirolimus treatment before we identified the ARAF mutation. In our pipeline, we have sequenced 103 additional patients with the complex lymphatic anomaly. We also sequenced the blood sample for all the patients and their available family members. In total, we identified pathogenic or likely pathogenic variant in 20 patients, which results in about 19% of molecular diagnosis yield. Additionally, we have identified a few VUS variants, and we are performing function study in the lab for the 20 diagnoses. PNP11 is the most frequent finding. As you can see, a few genes are converged on the RAS MAP kinase pathway, as we previously described, and the complex lymphatic anomaly presented in Noonan or Noonan-like patients. Interestingly, we also found some lymphedema genes in patients with channel type lymphatic anomaly. Next, we focus the somatic variants by deep exome sequencing and ultra-deep targeted panel sequencing. First, for patients with the tissue samples, we perform the deep exome sequencing. As you can see, with the 300 to 500 folds coverage depth, almost 100 percent of the exome region would have at least 100 folds, and about the 90% of the exome region would have at least 250 folds, which is a decent depth for us to discover somatic variants with a variant allele frequency greater than 2%. Indeed, we identified two pathogenic variants in KRAS and PI3CA in two patients with CCLA. This expands the causal pathogenic variant causal list, gene list for the CCLA, in addition to 3 genes that we have previously reported before. For the PI3CA patient, before we identified the variant mTOR inhibitor, everolimus and sirolimus were attempted, but it has only partial response. With the identification of PI3CA variant, the patient switched to PI3K inhibitor alpelisib, which significantly improved the symptom. Lymph drainage and her ascites decreased. This highlights a success with the molecular-guided clinical management. To validate the somatic variant, the ddPCR would be the gold standard, but it's pretty expensive as you would need to order every assay for every candidate variant. So here we use the blocker displacement amplification method, which is very affordable compared to ddPCR. Briefly, the blocker is designed to be perfectly match the known wild-type template. Primer and the blocker would have a 6 to 14 nucleotide overlaps, so they could compete for binding. The blocker is designed to have a positive free energy to wild-type and a negative free energy to the mutant allele due to a mismatch bubble. This will result in a difference in amplification efficiency in each PCR cycle. It was reported in 2017 that 45 PCR cycles would result in over 1,000-fold enrichment of variant allele. As you can see, by using this blocker method, for example, we confirmed the variant in the tissue sample with the mutant allele being predominantly present in the Sanger trace. If we can get the tissue samples from the lesions, we have a great chance to find a somatic variant. But for many lymphatic anomaly patients, there is no clear-cut tissue to sample. We were wondering if endothelial cells isolated from perfusion would be an alternative, and also cell-free DNA isolated from the fluid sample and the blood. And due to this sampling method, the variant allele frequency could be significantly lower than that in tissue. So we developed 2 panels for ultra-deep targeted sequencing. Again, 80% of complex lymphatic anomaly are unsolved molecularly. We were wondering if lower variant allele frequency variant may escape deep exome sequencing. So in this Illumina amplicon panel, we put together 35 genes and sequenced a really high coverage depth, 60,000 to 90,000. In the pilot study, 26 DNA isolated from endothelial cells from a fluid sample after CD31 selection were included. We were able to identify 3 patients having positive variants in PI3CA and KRAS. Interestingly, as you can see, 2 patients having the same KRAS variant have a very different variant allele frequency, reflecting the sampling variability. Again, we got this confirmed by the blocker method. Most recently, we upgrade the amplicon panel with the UMI method. Lower frequency variants, for example, less than 1%, are often confounded by PCR and sequencing error, as shown on the top left panel. UMI, on the other hand, will add barcodes to every molecule. This would allow us to do error correction by by combining the reads based on the UMI information and then covariant with the confidence on the consensus sequence. In our pilot experiment, we sequenced every sample to 60,000 folds, and we were able to get the decent coverage depth for the target region. This is summary for a few samples that we tried on different platforms, including a broader range of vascular anomaly phenotypes. As you can see, deep exome sequencing at current depth have trouble to confidently identify lower allele frequency variant, whereas amplicon panels seem to have trouble handling indels. UMI methods seem to be good at both situations. Of course, more data would be needed to confirm this. Last but not the least, in collaboration with Dr. Uh, Guy Choward from Israel, we use the ddPCR in self-free DNA sample to identify variant in NRAS for KLA patient. It's a recurrent variant in KLA and GLA. Due to the high efficiency of the blocker, the mutation allele is predominantly present in the Sanger trees. With this, I would like to acknowledge colleagues listed here for their amazing contributions. Dr. Adams and Dr. Hawkinson co-lead a vascular anomaly frontier program at CHOP and funding resources. Thank you so much for your time and appreciate any question that you may have.